Ready for the second part? Good.
Sorry, we have to
Switch it.
You have to remove the microphone.
It's topologically impossible.
Yeah. Topological search. We have to do a topological search here. No, you don't need to. Okay, it works. Thank you so much. Sorry about that.
It's fine. Okay, welcome back. Clarification concerning the dinner. There have been questions. So you're invited, but not for the cocktails, for the drinks. I think there will be one soft drink included or something like that in the dinner, right? Yeah, probably. We don't know yet. But no cocktails, this we know for sure. No drinks. The food, yeah, barbecue. The list is back there. We pass it around again in case you missed it. Sign up for it. Okay. Yeah, it's the dinner list. Okay, there were a few questions during the break. So some of them were connected to my handwriting. So if you cannot read what I'm writing, please feel free to ask immediately. What does that mean? And also, if I'm too quick, or if you want me to explain some calculation or some notation again, then please feel free to ask. Okay. Otherwise, maybe you have been discussing, and there are some more questions now. Then please go ahead. Otherwise, I will continue with the second part. Okay. So, yeah, we are going to look at another construction of a learning algorithm, which is based on this geometrical insight about the perceptron we had before. So we look again at a two-dimensional feature space. So n is 2 here. N is equal to 2. And let's say we have, and for simplicity also, we set the threshold to 0. So let's say we have already presented a lot of data to the network, and we have a plane here which separates a region where everything is classified as +1 from a region where everything is classified as -1. And then we present an example to the network where actually, let's say, it's this one here. So here, this is a +1. So you see it's on the wrong side. With a current vector, the network would classify it as -1. So what we need to do is, we need to move this separating line here a little bit in that direction. We rotate it like that, right? And we can do that by adding a small correction to the W, let's say in that direction. Okay, that would rotate the vector in that direction and the whole plane in that direction. And you see this here is the vector we are looking at right now, x mu, and they are in the same direction, as you can see, the correction and the vector itself. So it means that for this thing I just sketched, the correction would be proportional to the pattern we just presented. Okay, that would give the right thing. In that situation, the other possibility is where something is classified incorrectly, where now I should sketch it in a separate sketch actually. Yeah. Let's do another sketch of that. Or maybe I will try. So the other possibility is okay, do it again. So we have the same situation, like here and here. The W +1 -1. And now it's like that. Here, this is +1. So this would also be classified in the wrong way. And we see in that case, you want to rotate the plane in the other direction, that way. Okay? And we can do that again by moving the W in that direction a little bit. And it's again in the same direction as the X mu. So it's also here proportional to X mu. Okay? So now what about the patterns that are negative? So for instance, this situation here, that I have one which is -1. So in that case, I want to no, it was right. I want to move the plane in the same direction like before. Right? I want to rotate it that way. And the pattern I presented is this one here. This is the vector X mu. But you see, the correction now is not in the same direction. It's in the opposite direction. So there's a minus in front. But the pattern itself, it's classified as minus. So I can actually write down here that this is proportional to the training output, the training pattern times X mu. Because if this is positive, we're still back to that situation. If it's negative, then it's this situation. And the correction goes also in that direction. Okay, and you find the same thing here. If we are having a pattern that is misclassified on that side, you also want to move like that, but it's the direction opposite. So also here, you have the same correction. You can correct it with the target output of the pattern. Okay, and these are all the cases there are in that situation, which means that we can choose delta W proportional to learning rate, again, ST mu X mu. And this is something that people, this is a proportional here. This is something that people call the HEP rule, because it's inspired by neurons that fire together, wire together, in the way that this is S times X, so the output times the input. Okay, they work together. So this is just from the geometric construction, but we want, of course, that the algorithm should stop once it's done. So what we choose then, so we want the algorithm to stop if all patterns are classified correctly. So what we do is, to achieve that we simply subtract the S mu here. Because now it's the same as before, the correction, but if it's correctly classified, it doesn't do anything. It only corrects those that are misclassified. And now look at this here and at this here. And they're basically the same from a very different construction and reasoning. This here, it works, but it's not the algorithm that has been suggested originally. The common alternative for this to make the algorithm stop when it's done, and this is called the Rosenblatt perceptron algorithm. Is to do the following: delta W is equal to eta times theta C minus W x mu st mu times x mu. And this here, this part here is the Heaviside step function. So this is 0 if the argument is negative and 1 if the argument is positive. So it does this at the point C here. And the idea is that even if a pattern is misclassified, but even if a pattern is correctly classified, but very close to the boundary, you still do corrections because you want to counteract noise very close to the boundary. And this here, this algorithm, it can be shown that it converges. So it can be proven that this here finds the solution if there is a solution. And this is called the perceptron convergence theorem. And I present it without proof, don't worry. It's one of the most important and fundamental results in that area, which actually showed that these things can do the job. So the statement is, for linearly separable data, x mu st mu mu 1 to p examples, the Rosenblatt perceptron algorithm stops after a finite number of update steps, learning steps, and yields a weight vector v, w, with VW times x mu times st mu is larger equal to c, which can be chosen larger to 0 for all p. Mu, I mean, mu 1 to p. Okay, so if you find through this algorithm a W that fulfills this condition, it means that it classifies all the patterns correctly. It may well be that you have to represent the training pattern several times for the algorithm to succeed, and in random order or in batches. There are different alternatives. And typically, if you present all of the patterns once, this is called an epoch in machine learning. All the training patterns represented once to the network. It's called. The condition here? Yeah, for linearly separable data, the Rosenblatt-Percy-Terminal algorithm stops after a finite number of update steps and yields a weight vector W with W times X times ST larger equal to C, larger 0 for all mu. C is a constant that I can choose, and it fixes how far away from the boundary I do corrections here. So, but if I choose a C, I will find a solution for separable, linearly separable data. So nobody asks now, what is linearly separable data? That's the condition. And that means that what it is that actually the data is arranged in this feature space in a way that I can find a dividing line, or in higher dimensional space, a dividing hyperspace, right? Because if this does not exist, if the data is arranged in a way that this does not exist, the algorithm cannot find it if it's not there. And that's the condition. That is what linear separable means. It's a very important condition, and it seems to be very restrictive. I have presented in the beginning, as an example, the logical AND function, and there are several more logical functions, Boolean functions, and one of them is the logical exclusive OR, XOR. So it's again x1, x2, and the ST with +1, +1, -1, +1, +1, -1, -1, -1. So it's the OR function, but it excludes the case when both of them are +1. So this is -1, this is +1, this is +1, and this is -1. Okay, if I sketch that, it's a very fundamental and simple function. If I sketch that here, do the classification, I have a -1 here, a -1 here, +1 here, and +1 here. So anybody who sees how to draw a line here that separates +1 and -1? It's not possible, right? Exactly. So this is an example for data which is not linearly separable, which the perceptron cannot learn. And actually, this was quite frustrating for the people at the time they started working on it, because it's such a simple thing, and it cannot learn this simple rule. And yeah, it's characteristic in a way for the restrictions of this extremely simple network we have been looking at. It's just too simple for general tasks. We also have seen that for the linear, in the case of the linear activation function, the data needs to be linearly independent. It's also a quite strong condition if you think about it, that you cannot have more data than the dimension of your space. So, and it's typically in practice not like that. So we need, actually, there is a need for more general, more powerful networks. And the first thing you can do is to go to multi-layer perceptrons. So, meaning feed-forward networks with hidden layers. I think I will skip this here, continue here. Yeah, so the next thing we will look at is multi-layer perceptrons and what they can do. So we had already sketched them. You have an input layer here and inputs, and then you can have, in principle, arbitrary many hidden layers, and at some point you have an output, maybe 1, maybe 2. It continues here. Something like that. So this here is the input layer, the one to the left. These are the hidden layers. And here is the output layer, the one furthest to the right. And these kind of networks, they can learn much more general problems. In particular, also these kind of problems, which are not linearly separable. And they have become quite common in modern architectures, like convolution networks, deep learning, and things like that. Okay. So I will try to show you how they can, why they represent a generalization of the simple perceptron, what they do differently. We will again use the geometrical intuition we have here, generalize that a little bit, and other things too. I need to fix the notation for that. So what I'm going to do is, the output is still an x, and the index I is for the different inputs here, 1, 2, 3, 4, and so on. And the hidden layers, I call them Y. The values that the neurons take here in the hidden layers. Y, also I for the different numbers. And then the hidden layer gets an index L in parentheses at the top. So that means that the first one is the one with index 0. So xi is the same as yi0. And the last one here has a capital L, yi capital L. So that's the largest one. Capital L is the number of layers in total. And the connections here, they are now matrices W, J, I, so I should write J's in that case here. So it goes from I to J, that's the notation, so that I can write it as a matrix product. And the first one has a 1, and the second one has a 2, and so on. And the last entry here has a L as an index. So the last level, the last layer of connections. So that means that, and all these have activations functions. That means that I can calculate the yji of L as g of the sum over I w ji L times y I L minus 1 minus theta j L. Okay. Everybody following here? So you calculate the output of a certain hidden layer from the output of a previous layer, which is the input for that one. You weight it with a weight vector at that layer and the threshold here, which can now in general can be different for the different neurons, and it also depends on the layer. Okay? So let's look at an example. Just one hidden layer. It's always nice to start simple. And n equals to 2. So we look at this network here. We have 3 neurons in the hidden layer. They are all connected. And then we have one output layer here. And the output here, yes, by the way, this is the SL here. So here is SK. In that case, K is just 1 always. And I also, because I don't want to take the indices for the layers, I have small w here and large W in the second layer for that special case, yj xi. So this is my notation here. And you see now, if you look carefully, that actually in that network there are perceptrons hidden. So one is this one here. You see, the second layer to the output layer is a perceptron. But also each of these things here is a simple perceptron. This, for instance, you see. So in that sense, the more complicated network here is built up from the very fundamental perceptrons. Okay, and now I would like to show you that this network can be used to learn data which is not separable in the two-dimensional feature space. Okay, we have, okay, do it in a different way. We have the following distribution of input patterns. So these are plus ones, and then I have minus ones. They are, let's see, here. So you see, I cannot really draw a dividing line here, but I can draw like 3 lines, roughly. See, like that. This is one. There's one more pattern here. This is one. And this is one. And actually, I can choose the weight vectors in the first layer that these separating boundaries correspond to the 3 different neurons in the hidden layer. Namely, this here is W1, this here is W3, and this here is W2. And they are defined, this W with an index, in the following way. It's the matrix, it's a vector WY1, WY2, WY3. No, Y2. It's just, yeah, no. Okay, and now I will try to classify these resulting outputs in the hidden layer. So this is Y1, Y2, and Y3, and compare it to the target ST, which is in this picture here, coded by the color and the shape. So I have the possibility to have 1, -1, -1, -1, or +1, -1, -1, -1, +1, -1, -1, -1, +1, +1, +1, -1, +1, -1, +1, -1, +1, +1, and +1, +1, and +1. These are all the possibilities. So Y1 is the output produced by that weight vector. Y2, the output produced by that vector. Y3, the output produced by that vector. If all of them are negative, it means that they are on this side of the boundaries. So actually, they are up here. This is the outcome that is from all these 3 upper parts. And this is classified as -1 here. These are only -1 patterns in that regions, nothing else. Then you have +1 from the first one, it means it's down here, and -1 from the other two. It's up here, and there's nothing there. So this is empty, does not happen. Then, yes, the +1 here is down here, and the -1, it's up here for this one and for this one. So for both of them. So it's up here and at the same time down here. So it's something that has no overlap. So then -1 in the first one is up here, +1 in the second one, down here, and -1 in the third one, it's up here. So it's this region. It's -1. The classification, no, here. This one does not exist, we said. Then -1, -1 down here, and the third one, +1 up here. So it's +1. It's this region here, which is part of the +1. There's a pattern here. Here, should look like that. And then +1, +1, and -1. No, this is exactly what we did here. Wait a second. -1, -1, here, and +1 here. Yeah, it's also +1. And then -1, +1, +1, it's up here and down here. So it's this one, it's also +1. And -1, +1, +1 is also +1. And the last one, all downs, +1 is also +1. Now this one here is actually wrong. Let me see, -1, -1, and +1. Yeah, it's this region here. So it's -1, exactly. Okay, so this here is now in three-dimensional space a set of input patterns which I want to classify using this part of the network from 3 dimensions into 1. And if I sketch that, now I'm getting to the limit of my abilities here to sketch on the whiteboard. I will try, because it's 3 dimensions. So you have basically a cube. Okay, and if I translate these points, -1, -1, -1, which is minus, minus, minus here, and it has a -1 like that. And if I translate these points to all these corners in the cube, which are minus and plus ones, I get the following representation. Provided I did it correctly in my notes. And here you see there's one missing, that's this corner here. It corresponds to that, which is not there. And now you see that actually this thing here, you can imagine you can put a plane in here. So this representation is actually linearly separable in 3D. So that means you can find a weight vector which classifies that. So this network can classify this kind of data. So it does something like, in effect, it does something like constructing a boundary which looks like that. Okay? Combining these 3 boundaries. Yes? Okay, yes, I can. You mean this to this? Yeah. So what I'm using is that, can you see these boundaries here that I sketched? This one and this one and this one. So I'm using our geometrical insight we had earlier, so that each of these perceptrons represents a weight vector which separates the plane into two regions that are classified +1 and -1. On this side where the weight vector is pointing to, it's always +1. On the other side, it's -1. So for instance, for just this plane here, everything that lies below here is classified +1. Everything that lies above is classified -1. And then I combine all these three things. For instance, here, I have an output that is classified -1 in the first layer. That means it's above that line, because this is W1. So it's this area here, this one, and then it's also classified -1 for the second thing here. So this is this area here, and then it's also classified -1 for the third layer. So it's only remaining intersection is this area up there. And in that area, I see that the patterns that are located in there are classified by -1s. And this I did for all the different combinations. Is it clearer now? Okay. And then for the second layer, I translate this here in the three-dimensional, like hidden feature space into this picture here. These are the y's, the y direction. This is y1, y2, and y3. These are these three things, and you have -1, -1, -1, which is that point here, and then it is classified by -1. And if I mark all the corners in that way, I see it's actually linearly separable. Okay? Yes?
Sorry, I'm trying to understand what n equals to means there, because is then the number of features, the number of layers?
No, it's the number of input, the dimension of the input. It's dimension of the input. So here it's 1, 2. That means that n is equal to 2. It's the dimension of the actual feature space where I have the patterns. No, it's not the number of. No. Yes, it's the number of dimension of the input space. Are there more questions? I know it takes a little bit of time to wrap the head around this. I had this problems. But it's interesting because I think it's still interesting because it's a relatively simple construction, and you can see that the network actually is able to separate more complicated boundaries. And you can easily imagine that if you add more layers or more neurons, the boundaries can become more and more complicated. And you can actually train way more complicated data distributions than what is possible with a perceptron.
So in a sense, the dimensions, the input is in a two-dimensional space, but the hidden layer is in a three-dimensional space, and that makes it separate.
In that case, exactly. So the question here was that the input is in a two-dimensional space, but it's not linearly separable. Then the hidden layers augment it to 3 dimensions and make it linearly separable, and then you can classify it. In that example, yes. But interestingly, the XOR example can be classified with a network which has a hidden layer with just 2 neurons. So I was tempted to skip that example because Time is running fast, but maybe I should show it, right? I see some curiosity signs here. Okay, so let's have a look and see how a network with a hidden layer with 2 neurons can classify this problem here. So the network looks like that. It has 2 input neurons because I'm in 2-dimensional feature space. Then it has 1 layer with 2 hidden ones. They're connected like that. And then it has 1 output neuron. So in that case, I also need to use thresholds. And what I do is I learn the thresholds in a way for the first layer that there is 1 separating plane here. So this is W1, and the second one is here. W2 and also theta 2, and here it's theta 1. So I have thresholds and weight vectors that give these 2 separating lines. Okay, I can imagine I have a simple perceptron here that does it, and another one that does it there. Okay, so now same construction. Now I can look. If I go to the Y here, Y1, Y2, and compare to the target, how does it look like with these layers? So I have -1, -1, +1, -1, -1, +1, +1, +1. So let's have a look. -1, -1 means it has to be on the negative side of both lines here. So it's down here. It's just this pattern. It's a -1. +1 is on the side of on the plus side of the W1 plane, and minus the second column on the negative side here. So these are the 2 ones that are classified with +1. Then I have +1 here and -1 here. So there is no intersection of these areas. It does not exist. And then I have +1, +1. So they are classified on both sides here. And this is a -1. And if I translate that now, sketch that in the Y plane, in the feature space of the hidden layers, so to say, then I have 1 here, -1, -1, +1. So I have -1, -1 gives -1. So this is this here. +1, -1 gives +1. +1, -1 +1 does not exist. +1, +1 gives also that. So and then I see immediately that any separating line like that can classify the problem. So from here, from the Y space to the output, I choose a weight vector that gives that separation of the plane here. And then I can classify the XOR problem with this kind of network. 1 hidden layer. And I don't even need to go to higher dimensions. So it's not a general rule that you need to do that. Okay? So the question is, if I, after seeing that, now we have seen, okay, there's one hidden layer here, I need one hidden layer here. So it seems that one hidden layer corresponds to like one little bump in the separating plane. If I do more, maybe there are more bumps, it looks more complicated, and it's most likely like that, it's plausible. So how many hidden layers do I have to choose for a given problem? And the surprising answer comes from what is called universal approximators. By changing the perspective a little bit and look at these feed-forward networks as function approximators. So objects that approximate a function. Because I can say that my hidden network maps an input in n-dimensional real space, the xi, into just a real number. And that is what a function does. So now I ask the question, if I have an arbitrary function from Rn to R, can I find a network that approximates this function? Okay? And the answer is, it turns out that one can approximate any function to arbitrary precision with just one hidden layer. And this can be proven. And the question I have now is, I think we started a little bit later, right? I don't give you the proof, but I give you a flavor of what one is doing to actually show that the networks can approximate functions. The idea is that one approximates a function by summing over a set of basis functions. We have seen in the presentations earlier, the Fourier transform was mentioned, and one can, for instance, approximate functions by Fourier components to arbitrary position. And so what I do is that, so I want to approximate this function, and this, what I want to choose or find a network that can do that. And the common concept is approximation by a suitable superposition of basis functions. So that I write the function f of x as the sum of some coefficients and some basis functions. Yeah, and the question is, what are good basis functions for networks to represent? I start with dimension 1, so I look at functions that go from R to R, and the basis functions that one uses are these ones here. They look like that. Here they have a certain height, say W, and this is theta 1 and theta 2. Okay, and you can imagine that if you have any function that goes in R1, you can scale and change the height and superimpose these kind of pieces to piece together the function. And if you make them smaller and smaller, you can reach arbitrary precision. Okay? The question is, why these kind of basis functions? Right? Why do I choose these ones here? Anyone who has an idea? Sorry? No? It's always a good argument that you choose things that you can manipulate mathematically in an easy way. I agree to that. But here, the thing is that we want to represent the basis functions through networks and their activation functions. And here, the thing is, if I sketch that in a different way, then you will see. If I make it like that, I have one function that is this one here. Does that remind you of something? Yes. And then I have a second function that is this one here. Okay? And you see the difference of these two gives the blue one. In other words, I use as an activation function the sigmoidal I wrote down earlier. This is exactly this shape, scaled, and then I can get my basis function as W times sigma of W1 x minus theta 1 minus sigma of W2 x minus theta 2. Do you see that? So this is the sigmoidal. This here is the green one. And from the green one, I subtract the red one. And then I get the blue one. And the height is controlled by the W in front. And this here, I can express as a neural network with there's X. I'm in one-dimensional feature space. So I just have one input neuron where the X comes in, but I have two activation functions with different W's. So I have two hidden neurons in the hidden layer. And there is the W1 here, W2 here, theta 1 here, theta 2 here. And then they are combined into one output neuron simply by the linear activation function. This is just linear. And here in the middle, I have the sigmoidal. So this network here creates the blue basis function. So, and then if you change the thetas and the W's and build a larger network of many components of these, you can construct. It's plausible that you can construct any function you want to arbitrary precision, right? Yeah. Then you can do the same thing in higher dimensions with an additional twist, because I will just sketch it. I will not write down the formulas now because it's already quite late. So the idea is basically the same. You have the sigmoidals, which you subtract from each other to get regions that are selected by the sigmoidals, and in 2 dimensions, if you have 2 input neurons, it would look like that. So here you have, for instance, in the x1 direction, you have selected this region here. So this is sort of a top view now. So the function goes like that. Okay? And then for the second direction, I do the same thing in a different way here. So I have another basis function which goes like that, out of the plane. And then I really construct it from these elements. So for 1 dimension, here I do this. It's the same element, and do that for the second dimension. So here it's x1 and x2. And here I have, in the middle, I have the sigma activation function, and I have a vector y. And then they are all, I mean, I want to produce one, here this is always just real numbers. Okay, so they are all combined into one output. Also with the sigmoidal, you can, because you want to choose that region in the middle here, and here the thing is, if you think about that, if you try to imagine that this function here goes like that, and this function goes like that, that means that this cross in the middle, the square where the both cross, it's counted twice in a way, while these are all counted just once. And this additional sigmoidal here selects out the region with the highest weight. You can do that by adjusting the threshold between 1 and 2, so to say, here. And then you just select out this. And in the end, you add the linear layer, like here. Okay? But in higher dimension, you have to have these intermediate steps to choose out the area that is counted n times. And this one can write down in formulas, which I spare you now. So does that make sense? So you see by construction, it's rather plausible that you can approximate any function through a multi-layered neural network. And then one can prove, as the universal approximation theorem, that any continuous function can be approximated to arbitrary accuracy by a network with a single hidden layer for sufficiently many neurons in the hidden layer. But the theorem doesn't say anything about how many neurons you need. It can be really many. And that's the problem. That's why we choose to train networks with many hidden layers, because they also can achieve that, but they are better to control and better to construct rather than a huge network with one direction. It's just a mathematical theorem that says it's possible. Doesn't mean that it's practical. And this thing then, building these multi-layered networks with many hidden layers, leads to the concept of deep learning, feed-forward networks. And this is something we're going to discuss tomorrow. Any more questions? Questions, questions, questions.
From what I understood, I did understand.
So you have a question here or? No, okay. Okay, before I take your question, Oliver asked me to put this up for his classes tomorrow. If you want to follow, you can install something on your laptop beforehand to be able to follow. Would you want to say something? Great. So there was a question.
Yes, I was trying to understand better the theorem that you exposed just, that any function can be explained through just one hidden layer or with many multi-perceptron layer, I don't know, algorithm or architecture. Because if you can draw, for example, a graph from time series, what I'm trying to understand is, can we assume or can we identify these structures because we already know all the points in the future? I mean, for example, if you draw a function, any function, for example, the exponential function, you will know prior the architecture, all the points in the function. You already know all the information. But in functions, on more complex functions or in more complex equations, we are not going to know what is going to happen in the future. So that theorem that you already presented us is related to that?
No. So this theorem, it simply says, let's say I'm looking at functions R to R. And what I did not emphasize is that it's actually not whole R, but it's a compact subset, okay? So it's from a subset in R to R, where R is a subset of R. So you have a function that is somehow doing something on a set R, which is in R. And this you can approximate. Okay? But if you have a time series that goes on forever, then I don't think that theorem says anything about that. Does that answer a question?
Yeah, somehow, because we already know everything about the function.
In a way, yeah, we do. Yes, yes.
Essentially, all data is separable in infinite dimensions.
Exactly, in a way. You can learn anything if you put in enough neurons. Yes, yes. As said, I find it surprising that it's just one hidden layer. But as said, it can be really, really many, many neurons. You don't know. Okay, if there are no more questions for now, then we will conclude, and you're welcome to stay around and discuss with all the lecturers and ask questions. And yeah, thank you.